Hello students. Today we are going to study linear programming problem. It's a very interesting topic and it comes under operation research branch of maths. We are going to study the most easiest method to solve a linear programming problem, which is the graphical method. You must be wondering where it can be used. It's a relatively new topic and it can be used to solve problems of these type. It has very vast applications. Suppose you want to know that if a manufacturer of electronic items has a stock of say 720 resistors, 300 transistors, and it is required to produce two types of devices A and B. The requirements for both the devices is given, the profit for both the devices given. You want to know how many units of type A and B must be produced so as to maximize the profit. Remember this thing. So here you need to maximize the profit. So linear programming problem actually deals with optimizing something, whether it is maximizing profit, minimizing cost, and so on. Some definitions. An optimization problem is a problem in which we need to maximize or minimize a function, and the objective function is called the optimization problem. For example, as I said, you can maximize the profit, production, or you can minimize the cost, time, or any other resources. Now, a linear programming problem, it deals with optimization, means maximization or minimization of a linear function subject to some conditions. These conditions are fulfilled by some variables which are non-negative and they satisfy a set of some linear inequalities which are called constraints. We will see a proper standard form of linear programming problem. Basically, linear programming is a general technique of optimum allocation of source or limited resources, as I said, which can be material, capital, labor, machinery, etc., to several competing activities, which can be products, jobs, services, project, etc., on basis of some given criteria of optimality, which can be in terms of performance, utility, time, distance, etc. This is the definition. Basically, in very simple language, linear because the relationship is linear between the variables, and programming here means the economic allocation of the limited resources to achieve the desired objective. Now, the general structure of a linear programming problem, it is called LPP. It has four major parts. First is the decision variables, objective function, constraints, and the non-negativity constraint. So basically, what is the objective function? It is a linear function denoted generally by capital Z. And suppose if you are having just two variables, two decision variables, it will be of the forms of some ax plus by, where a and b are constants. And this objective function needs to be maximized or minimized. Decision variables are x and y, whose values will give us the optimum value of the objective function. Constraints means there are some linear inequalities, or you can see some restrictions on the variables. So they are called constraints. First, the LPP is formulated and then it is solved using different methods. Here we are going to study the very basic methods, graphical method, and remember, graphical method is obviously used when the number of decision variables are 2. For more decision variables, there are other methods like the simplex method which can be used. Now, the mathematical model of a linear programming problem, it is of this type. You have to optimize, means maximize or minimize z, which is c1 x1 plus c2 x2 plus cn xn, given to some constraints, or you can say subject to the linear constraints. These are some inequalities. Now, if you just observe this model, here cj's are the coefficient in the objective function, and actually they represent your profit, cost, anything per unit. That means if I say profit per unit of type A device is 10 rupees, so 10 into number of units will give you the total profit. So this is the per unit profit, or suppose if you are minimizing per unit cost. Xj, they are the decision variables. Aij are the input output coefficient, means the coefficients associated with the variables. On the right hand side, you have BI. These are the resources. That means the total availability of time, total availability of raw material. So these are the resources. Remember, here, since we are doing the graphical method, we are going to only study LPP consisting of two variables, but this is the general mathematical model for n variables. Now, since we are using the graphical method, we are going to discuss some definitions related to the graphical method. You will understand them better as we solve the example. First is the feasible region. You know, feasible means where your solution is possible. So feasible region is the common region determined by all the constraints, including the non-negativity constraint. And this is called the feasible region because your answer will lie in this region. Feasible solution. The points within and on the boundary of the feasible region of an LPP represent the feasible solutions. So that as we see the example, once you decide your feasible region and all the points which are there on the boundary of this feasible region will give you either the maximum or the minimum value, means the optimum value. Sometimes you can have infeasible solution. Infeasible solution is basically if you have any point outside a feasible region, it is infeasible. It will give you an infeasible solution. Optimal feasible solution is what you need to find. Optimal means if your sum is of maximization, the solution which gives maximum value. If it is of minimization, the solution which gives minimum value will be your optimum feasible solution. So now for using the graphical method, actually, there are two graphical methods, which is the extreme point enumeration method, or it is also said the corner point enumeration method, or the ISO profit or cost function method. We are going to use the extreme point method. So the steps in simple language, first step is you formulate the problem by properly defining your decision variable, objective function and constraints. Then you just graph the linear constraint. You know how to plot a line. So you just graph the linear constraints. Identify a feasible region and its corner points. Now there are some theorems, or you can say results, based on which it is said that your corner points will always give you your optimum value. So substitute these points into the objective function, and then from that, whichever gives the optimum value, that is your solution. Now we again take our example which we had discussed in the starting. In this example, the manufacturer has a stock of say 720 resistors and 300 transistors, and these are required to produce two type of devices, A and B. Type A device requires 2 resistors, 1 transistor. B requires 3 resistors, 1 transistor. If the profit on type A device is rupees 510 per unit and for type B it is 675 per unit, how many units of A and B must be produced so as to maximize the profit? So here your objective is maximizing the profit, and your constraints, or you can say the inequalities or the constraints over here, are in terms of the number of resistors and transistors which are available. So first thing is, it is very good to actually represent your data in the form of a table so that it becomes easy to formulate the objective function. So the type A device requires 2 resistors and B requires 3. Total availability of the resistors is 720. Similarly for transistors, profit for type A device is given and profit for type B device is given. So first you need to decide your decision variables. Here, suppose X and Y are my decision variables. They will represent the number of units of A and B which are to be manufactured. In order to optimize, here it is maximize the total profit. So now your objective function is maximize Z is equal to per unit profit 510 into number of units to be manufactured, which is 510x, plus same way for B device 675y. So Z is equal to 510x plus 675y is your objective function. Then it is subject to the following constraints. What are the restrictions? See, 2 resistors per device of type A. That means 2 into X. Total number of resistors required for type A. Plus, same way for B. the number of registers required for B will be 3 into Y. This total should be less than or equal to 720 because the manufacturer has a stock of 720 only. So the inequality will be 2x plus 3y less than or equal to 720. Similarly for transistors, X here only one transistor is required for both the devices. So X plus Y is less than or equal to 300. And one non-negativity constraint is always there in a LPP, which is your decision variables should always be greater than or equal to 0. What is the reason? Because you cannot have number of units as negative. So in our example just now we have seen we have to maximize Z is equal to 510x plus 675y subject to these constraints. This is our formulation of the problem. To use the graphical method, you need to plot your linear constraints. That means the first constraint is 2x plus 3y less than or equal to 720. So this line, if you want to plot, equation for the line is, first of all, you just consider this as an equality and plot the line. And then we will see the inequality for getting the feasible region. So the line is over here 2x plus 3y is equal to 720. So you know how to plot a line. You take some points of x, find the corresponding point of y. Here, if you want to find y will be 720 minus 2x by 3. Now remember some techniques how to get the points of this line. One thing is whenever you put x is equal to 0, try to get the value of y if it is positive. And another way, take the value of y as 0 and try to get the value of x if it is positive. Why I am saying positive or non-negative? Because non-negativity constraint will always be there. Your x and y should always be greater than or equal to 0. Now other points, how will you get? To get the other points, okay, by just looking at the problem, like over here, if x is 0, y 240, if y is 0, x 360. Suppose if x is 150, you will get a whole number for y, which is 140. So this is fine. But always take a point which gives the intersection of the two constraints, because generally your feasible region will have a corner point which will be the intersection of the constraints. So how to get that? See here which two lines are there. The second line is x plus y is equal to 300. As I said, first plot the simple point 0, 300, 300, 0, 150 and 150. Also plot a point which is the intersection of two lines. Actually, if you draw the graph, you will get this point automatically. But to be on a safer side, or you can say to verify your answer, how will you get this intersection point? Because sometimes the intersection point is in fraction. So from the first line, suppose if I have the first line y is 720 minus 2x by 3. Equate this to the y of the second line. It is 300 minus x. So this will give you the value of x as 180. Now x is equal to 180. Put in any of these two equations. You will get y as 120. So actually what we have done is we have tried to get a point which satisfies both the lines, equation of both the lines. So 180, 120 is the intersection point of these two lines. So it satisfies both the lines. This is how you get the points for the constraints. Now to get the solution, what is the method? As I told you, first of all, you can see over here we have plotted both the lines. Now both the inequalities are of less than or equal to type. So you have to take the region which is below both the lines. The region which is below both the lines is I have indicated over here. This region will constitute your feasible region. And your corner point, this is called the corner point method also. Why? Because you take the corner points and one of these corner points will give you the optimum value. So here you can see the feasible region, and the corner points of feasible region are O, which is 0, 0 origin. Then you have point A, which is 0, 240, point B, which is 180, 120, which is the intersection of both constraints, and point C, which is 300 and 0. So now at all these corner points, you have to find the value of your objective function. So put your value, say suppose point A, 0 to 40. So put x as 0, y as 240. You will get the value of z as 162000. Similarly for B, put x as 180, y as 120. So you will get 510 into 180 plus 675 into 120, which is 172800. From all these four corner points, point B gives you the optimum. Over here you need to find maximum value. Point B gives you the maximum value. So our answer is, if suppose 180 units of device A and 120 units of device B are produced or manufactured, then the company will get the maximum profit, which is 172800. So I hope the method is clear. We will do different type of examples. Second example is, a firm has to transport 1200 packages using large vans which can carry 200 packages each, and small vans which can carry 80 packages each. The cost for engaging a large van is rupees 400, and for one small van it is rupees 200 per van. So one more constraint is given, not more than rupees 3000 is to be spent on this job, and the number of large vans cannot exceed the number of small vans. First you have to formulate this problem and then you have to solve it. That means find the minimum cost. So first of all, what will be your decision variables? Suppose x and y are the number of large and small vans which are required. So these are your decision variables. Objective function will be, you have to minimize the cost. Cost for one van is 400. 400 into number of large vans, which is 400x. Cost for small van is 200. So 200 into y, which will give you the total cost for small vans. So you have to minimize z, which is 400x plus 200y. What are the conditions or the constraints? First thing is, 1200 packages have to be transported. That means minimum you should be having a capacity for 1200. So remember here the inequality will be greater than or equal to. Correct? 200 packages in one such big van and 80 packages in one such small van. So 200 into x plus 80 into y. These many packages you can accommodate, but the condition is this total should be greater than or equal to 1200, because minimum of 1200 is required. Second condition is, since the cost per van is given and for large van is given and cost per small van is given, then the total cost should not exceed 3000, means 400 into x plus 200 into y should be less than or equal to 3000. And third, one more condition is given, that the number of large vans cannot exceed the number of small vans. That means your x should always be less than or equal to y. It cannot be more than y. Or in other words, you can write as x minus y less than or equal to 0. And the last non-negativity constant will always be there. X and y are greater than or equal to 0. After formulating the problem, we need to solve it, but for that first we need to find the points which represent the three given lines. The first inequality is 200x plus 80y greater than or equal to 1200. Remember, both the sides you can divide by, say over here the common factor is 40. To make the inequality simpler, it will now become 5x plus 2y greater than or equal to 30. You can do this with the constraints, but obviously you cannot do it for the objective function. So over here, both the sides you have to divide by that common factor to make the calculation easy. The first line is 5x plus 2y is equal to 30. Put x 0, y you'll get 15. Take y as 0, you'll get x as 6. The third point, I'll show you why we have taken it when we see the graph. Second line, when x is 0, y is 50. Here if you take y as 0, you'll get x in fractions. So to avoid that, we have taken y as 1, so x is 7. Remember, you need at least 2 points to plot any line. The third line is x is equal to y simple. So whatever x value you take, the same y value you can get it. Now let us plot the graph. Now when we plot the graph, we have plotted the three lines. For the first line, it is greater than or equal to. So it will be above the first constraint line. For the second line, less than or equal to, so it will be below that line. And similarly, for the third line, it is again greater than or equal to, so it will become above the line. So when you consider the intersection of all the three things, you will get the feasible region as shown over here. Now see over here, if you take the feasible region, you get 3 points, 3 corner points for which you have to evaluate the objective function. 2 points are simple. First point say A, which is 0, 15, and the point C, which is 5, 5. So that is simple. But the third point which is there, you need to find this point. As I told you on the graph directly, you can find it out. But to get the exact value to verify your that point, what you do is manually also you try to solve the intersection of the two lines which are defined by this point, say over here B. So here if you look carefully, the point B is the intersection of the first and the third line. So now when you take this intersection, you will be getting the value of, just see over here, you will be getting the value of x as 30 by 7, and obviously so y will also be 30 by 7. So you would find this point of intersection on the graph and similarly verify it manually. So now you have these 3 corner points, and when you evaluate z at these 3 corner points, you can see the minimum value is obtained at the point B. So the optimal solution is 18,000 by 7, which is the minimum cost. It is obtained when the number of units for x is 30 by 7. That means the large vans is 30 by 7 and the small vans are also 30 by 7. Obviously, if you consider our problem, since the number of vans cannot be in fractions, you will need to consider the approximation. That means approximately 4 large and 4 small vans are required to minimize the given cost. Now the third example, and I have written the first case. Let us see why. A company manufactures two types of sweaters, type A, type B. It costs rupees 360 to make a type A sweater, 120 for type B sweater. It can make at most 300 sweaters in a day and spend at most rupees 72,000. The number of sweaters of type B cannot exceed number of sweaters of type A by more than 100. Company makes a profit of rupees 200 for one sweater of type A and rupees 120 for each sweater of type B. First thing is formulate to maximize the profit and find that maximum profit. First, your decision variables will be the number of sweaters of type A and type B to be made. So, what is the objective function? Maximize the profit. Maximize Z is equal to 200 per unit. So, 200 into X plus 120 per unit of B. So, plus 120 Y. Subject to the constraints of what are limitation? First limitation is 360. It costs 360 to make one sweater of type A. So 360 into X, total cost for A type sweaters, plus 120 into Y. This should not exceed, it can spend at most 72,000, means it should be less than or equal to 72,000. Again, as I told you, you can take out the common factor to make it simpler. So the inequality now will become 3x plus y by dividing by 120 on both the sides, less than or equal to 600. Second case is that number of sweaters cannot exceed 300. That means total x plus y should be less than or equal to 300. Third condition, number of sweaters of type B cannot exceed number of sweaters of type A by more than 100. That means your difference of y minus x, type B sweater minus type A sweater, should be less than or equal to 100. It cannot be more than 100, means it should be less than or equal to 100. That means y minus x should be less than or equal to 100. Or x minus y greater than or equal to minus 100. Both the things are same. And last thing is x and y should be greater than or equal to 0. This is the non-negativity state. Now to plot the graph, we need to find out the points representing the three lines. So again, first line 3x plus y is equal to 600. When x is 0, y is 600. When y is 0, x is 200. One more point I have taken, which is 100 and 300. Similarly, the second line. And similarly, the third line. So just try to get at least 2 points for each line so that you can plot all the three lines. Now, the most important thing is getting the feasible region. So, first inequality is 3x plus y less than or equal to 600. So, all the points which are below this line, 3x plus y is equal to 600, will be there in the feasible region. Second thing is x plus y less than or equal to 300. So same thing, all which are below this line will be in the feasible region. Now for the third constraint, sometimes these type of constraints make it difficult to understand. I'll tell you a very simple trick for this. The third line is x minus y greater than or equal to minus 100. Now, if you want to decide on which side you have to consider the feasible region for this line, what you do is always you take your x and y as 0, 0. So, if I take x as 0, y 0, 0 minus 0 greater than or equal to minus 100. Is it true? Yes, 0 is always greater than or equal to minus 100. So now all the points on the side of this 0, 0 means the origin will constitute your feasible region for the third line. So whenever this type of problem occurs, very easy technique, it's a best technique. What you do is you just take the origin values means 0, 0, put it in the given equation. If it satisfies the inequality, like over here 0 greater than or equal to minus 100, then it is on the side of 0, 0. If it does not satisfy that inequality, it is on the other side of 0, 0. So this is how you get the feasible region. Then the intersection of all the three will give you this feasible region. Now if you see over here, it has 5 corner points. First is obviously the origin 0, 0. Second one is 0, 100. Then you have 100, 200. You also have a point 150, 150. And the last point is 200, 0. Again, for getting this point 150, 150, you just see it is the intersection of the two lines. So you can get it from the graph, or as I have shown it over here, you can also manually check whether it is the point value is right or not. So the next point is 150, 150, or at all these 5 points, you just put it in the objective function. Here you need to maximize the profit, whichever gives you the maximum value is your answer. So the maximum profit is obtained of rupees 48,000 by producing 150 units of type A and 150 units of type B sweaters. I have taken the same example, but the second way how it can be used. See, the example is same, only one difference is there in the same example. This is to illustrate how the feasible region matters. So I have taken this example, the second part. In this part, what is different over here is the company has to make at least 300 sweaters. Correct? There it can make at most 300 sweaters. So here, since the company has to make at least 300 sweaters, the second inequality will become x plus y greater than or equal to 300. If you remember, in the first case, it was x plus y less than or equal to 300. So only this difference is there. Now let us see how it makes a difference to the solution. Next, we plot the points. The points will be same because we are plotting in form of lines, equalities. So the points which we have used previously, the same points we are using it. Only the difference will be in the feasible region. And as I told you, if you want to find over here the point of intersection, you will be needing this when you see the graph of the lines 3x plus y is equal to 600 and x minus y is equal to minus 100. The same technique, equate y of both the lines and you will be getting the value of x as 500 by 4, which is 125. When you put it in any of this equation, you'll get y as 225. So you get a point of intersection of these two lines, 3x plus y is equal to 600 and x minus y is equal to minus 100, which is 125, 225. Now when you plot the graph, the three lines remain the same, but your feasible region now changes. Because of the second constraint here, the second constraint is x plus y greater than or equal to 300. So the values which are the region which is above this line will be included in your feasible region. There it was below this line. So now when you consider the intersection of all these three feasible regions, you'll get the feasible region for the whole problem which satisfies all the three constraints. And now this feasible region has only 3 corner points. So you can see how the whole sum has changed if one inequality is changed. There you are having 5 corner points, here you are having these 3 corner points. So First point 100, 200, next point 150, 150, and I had told you before that I have found one more point which is 125, 225. The reason for this is because it is the intersection of these two constraints. So now when you evaluate your objective function at all these 3 points, the maximum value is obtained at 125, 225. So the answer is the maximum profit of rupees 52,000 is obtained by producing 125 units of say type A sweater and 225 units of type B sweater. Now see, some special cases can also occur value solved by the graphical method. We will take one example for each case to understand it properly. First thing is sometimes you can get multiple optimal solutions. We will see this with the help of an example. That means suppose if two corner points are there, both will give you the optimum value and both lie on one particular line. So in fact, both these points, including any other point on this line segment, will give you the optimum value. So this type of problem will have multiple optimal solutions. Second case can be unbounded. That means suppose your feasible region is there. One constraint is of less than or equal to type, another is greater than or equal to type. So you get a bounded region. But suppose sometimes you have the constraints in such a way, inequalities in such a way that you will get an unbounded region from one side. Then in that case, you might not be able to obtain the maximum or the minimum optimum value because the region is unbounded. Infeasible solution means basically no solution. When will no solution exist? If two constraints are there which both of them contradict each other, that means you cannot get a feasible region which satisfies both the constraints or all the constraints. In that case, you get an infeasible solution. Now the next example, I said that there can be some special cases. Let us discuss them. So suppose you need to maximize z is equal to 10x1 plus 6x2 subject to 5x1 plus 3x2 less than or equal to 30, x1 plus 2x2 less than or equal to 18, x1 x2 greater than or equal to 0. So the same technique for both the lines, first obtain the points to plot the lines on the graph. So again for the first line when x1 is 0, x2 is 10, when x2 is 0, x1 is 6. Similarly, for the second line, when x1 is 0, x2 is 9, when x2 is 0, x1 is 18. You can see you will need the intersection of these two lines. So how to get this intersection point precisely? Again, from the first equation, suppose anything you can equate either x1 or x2. So suppose from the first equation you have x1 as 30 minus 3x2 by 5. From the second equation you have x1 as 18 minus 2x2. So equate both the x1s. You can equate both the x2s also. In short, equate both of these lines. So you will be getting over here x2 as 60 by 7 and x1 as 6 by 7. So the intersection point you can see in the graph also will be getting of the two lines, which is 6 by 7, 60 by 7, which is one of the corner points. So you can see from the graph, you're getting 4 corner points for the feasible region, 6 by 7, 60 by 7, 6, 0, 0, 9 and 0, 0. Out of these, points A and B give the same objective function value, which is 60 and which is the maximum value. So two solutions you have obtained. This is the case of multiple solutions. Two solutions you have obtained which give you the maximum value. Now if you check out any point on this line segment joining points A and B will give you the same optimum value of 60, and so it can form the solution. There are infinitely many such points on line segment AB. So actually this is a case of multiple infinite solutions. Out of them, two you have obtained very easily by seeing the corner points. So it is a special case of multiple solutions. Now below I have given that in fact if you want to find the in terms of solution set, all the solutions you have learned previously, how will you represent the points on a line segment? So x1 will be, since the both the endpoints are, one of them is 6 by 7, another one is 6, so it is 6 by 7 into lambda plus 6 into 1 minus lambda. Similarly, x2 will be 60 by 7 into lambda plus 0 into 1 minus lambda, both the corner points, where obviously your lambda is any value between close interval 0, 1. You have learned this previously. So this you can apply to get the whole solution set. Next special case is for the unbounded solution. Maximize z is equal to 3x1 plus 2x2 subject to minus 2x1 plus 3x2 less than or equal to 9, x1 minus 5x2 greater than or equal to minus 20, x1, x2 greater than or equal to 0. Okay. Now the second constant which is there, it doesn't matter. Your values on the right hand side can be negative or positive, both the things. But generally when you write it in the standard form, your right hand side values you take it as positive. The reason is over here, there are other methods to solve these type of problems like the simplex method. In all of them, one of the requirement is the right hand side values which you are having bi values, they should be non-negative. So if they are negative, you can multiply by minus 1 on both the side of the inequality. So the given problem is same as I have written it in another form, in which the second constraint is written as minus x1 plus 5x2 less than or equal to 20. Correct? It doesn't matter, it is the same thing, but to make it in the standard form. So the next type of special case is the unbounded solution. Maximize z is equal to 3x1 plus 2x2 subject to minus 2x1 plus 3x2 less than or equal to 9, x1 minus 5x2 greater than or equal to minus 20, x1 x2 greater than or equal to 0. Now it's the same problem. The second constraint has negative value on the right hand side. It is okay. You can have negative. It can, the right hand side values means your bi values can be negative, positive, 0, anything. But if you want to solve by other methods, like for example the simplex method or so, one of the condition is your right hand side value should be positive. So if it is not, you can multiply by minus 1 on both the side and make it positive. So this problem, if I want to write in a generalized form, or you can say in a proper standard form, the second constraint I will write as minus x1 plus 5x2 less than or equal to 20. It is the same problem. Now we plot the points. And now to obtain the feasible region for the first constraint minus 2x1 plus 3x2, it is basically less than or equal to 9. Correct? How will you check on which side it is? Again, I told you the trick. Put your x1, x2 or both the variables as 0, 0. 0 plus 0 is 0. Is it less than or equal to minus 9? Yes. That means your feasible region will be on the side of 0, 0 of the given line. Same way for the second constraint minus x1 plus 5x2 less than or equal to 20. For this, if I want to check, if I put x1, x2 as 0, so 0 less than or equal to 20. Yes, 0 is less than or equal to 20. So it is on the side of 0, 0. So now when you get the feasible region, you can see it is unbounded physical region. So if I take over here this feasible region, it is unbounded solution which we are going to get. If you remember, to get the feasible region, I have taken one more point which is 15 by 7, 31 by 7. This is nothing but the intersection of the two lines because it is one of the corner points. Since the feasible region has no bounds over here and we have to find the maximum value, that means as you go on increasing on the right hand side, you will be getting more and more maximum values. So basically unbounded solution exists. So this is a case in which your feasible region is unbounded, so the solution is unbounded. The next case is for infeasible solution. Sometimes, as I told you, you cannot find a feasible region which satisfies all the constraints simultaneously. I have given this linear programming problem. In this, suppose if you consider the inequalities, that means the constraints, you can see that the minimum value x can take is 15 and y is 10. The third constraint, third and fourth constraint, x greater than or equal to 15, y greater than or equal to 10. That means minimum it should be taking 15 and 10 value respectively. Now if I put x as 15 and y as 10, in the second inequality, I will be getting 4x plus 5y, which will be equal to 110. But is 110 less than or equal to 20? No. So if I take this constraint, it will not satisfy the second constraint. So basically, you will not get a region which satisfies all the constraints simultaneously. So no feasible solution, or you can say no solution for the given LPP exists. See students, linear programming problem is a very interesting topic and it is very useful in further studies. So do like and share the video and subscribe to the channel.